Kinetics is the study of the speed of a reaction, how fast the reaction actually occurs. Thermodynamics, covered earlier, is a study of will a reaction happen or not. But kinetics is not whether it will happen, but when will it happen. Some reactions can be very fast, such as the reaction with copper sulfate and ammonia. Instant reaction causing it to go from the light blue color to the dark blue color. Other reactions are a little more slow. It takes some amount of time for the reaction to fully develop, as the light blue color is slowly progressing into the golden, almost pumpkin pie looking solution. And the kinetics of these reactions play an important role in chemistry of when a reaction will occur.
Kinetics is the study of the speed of a reaction, or the timing. How long will it take to go from reactants into products? So thermodynamics, covered a little earlier, studies if a reaction is possible or if a reaction can happen. Can you mix a couple of compounds together and will it form a product? Will a chemical reaction occur? Kinetics is based on the timing, not if a reaction will occur, but when will a reaction occur. And these two different studies of thermodynamics and kinetics play an important role in how chemistry happens and determines what types of products you end up with in a chemical reaction. Kinetics are not something that can be just determined based on the chemical reaction itself, just based on looking at the energies of the different reactants. You have to actually measure the time and measure the different rates of the reaction. In kinetics, there are two terms that are used a lot: the rate, or the reaction rate, and the reaction time. And these two terms are inversely related. That is, the rate is equal to about 1 over the reaction time. As the rate increases, there's a higher rate of reaction, a faster rate. That means the overall reaction time is going to decrease. The same thing would be true if it's a very low rate. If the rate of the reaction is very small, that means few reactions are happening over time, and therefore the time it takes for the overall reaction to happen will increase. While many times in the math of chemistry, looking at the chemical reactions, the rate is what would be used, that's not something that can be directly measured. But time is something that can be measured. And in labs and in experiments, you're measuring a reaction time, how long it takes to go from reactants to products, and then using this proportionality to convert that into the reaction rate itself. The rate of a chemical reaction is very much dependent on the concentration. Even a slight change in concentration can change the rate of a reaction drastically, depending on how, depending on the rate law and how the concentration is related. So typically you have reactions going from reactants into products. Reactants into products. The rate law is the mathematical equation that relates concentration to the rate and therefore to the time of a reaction. So the rate is equal to some rate constant, which would be unique for each individual reaction, times the concentration of each reactant. The kinetics and the rate of an equation is not dependent on the overall products, but it's dependent on the concentrations of just the reactants. So it's the rate constant multiplied by the concentration of the reactants, and these reactants are raised to some power. And that's not from the balanced chemical equation. These exponents, these powers, are the reaction orders of the particular reaction. The specifics of how the concentration will change and affect the rate. So a reaction order is something that truly affects the rate, the nitty-gritty of how changing the rate, or I'm sorry, how changing the concentration will specifically affect the rate itself and therefore the time. In many cases, if you double the concentration of something, you will double the reaction rate. That the reaction rate will increase by a factor of 2, and that means the time will decrease by a factor of 2, because if you have a high rate, the overall reaction time is small. In other cases, if you double the concentration of something, the rate will increase by 4 times. It will happen 4 times as fast, and the reaction time will be cut down to only a quarter. And there are even cases where it's not related to the concentration. This would be a 0th order reaction. So each of these different reaction orders is different based on the concentration or based on the different reactant. Many times you can, in chemical equations, there are multiple different reactants, and each one of them may have a different reaction order.
Reaction orders are specific to each different reactant. To check the reaction order, you can change the concentration simply either by cutting the concentration of one component in half or by doubling that concentration. In this reaction of sucrose and potassium permanganate, the sucrose concentration was cut in half. The dark purple permanganate still instantly reacts to form the green manganate ion. However, the timing of the second step of the reaction is now increased, approximately doubling the reaction time. By cutting the concentration of sucrose in half, the reaction time doubled, indicating the reaction rate was also cut in half. This would mean that in this second step of the reaction, sucrose is a first order reaction, and in the first part, it is a 0th order reaction, as there was no change in timing based on the concentration. How the concentration affects the timing of a reaction is referred to as the reaction order. Some reactions, if doubling the concentration, will cut the reaction time in half, thereby doubling the rate. This would be a first order reaction. Second order reactions, when doubling the concentration, would cut the time to 1/4, increasing the rate by 4. There are also zeroth order reactions that are not dependent on concentration. In this two-step reaction of potassium permanganate with sucrose, or table sugar, the intense purple color of the potassium permanganate instantly goes to a dark green color. Then, in the second step of the reaction, the slower reaction with a slower rate changes it into the gold color.
Based on that video experiment, you're looking to see how the change in concentration changes the overall time of a reaction, and the overall time is related to the overall rate. Most times, these are the three reaction orders that a lot of reactions would undergo, where you can either have a zeroth order reaction. This would be one where it is independent of the concentration. So in a zeroth order reaction, that means it's the concentration raised to the power of 0, and anything raised to the power of 0 is just 1. So if you double that concentration, it's still raised to the 0 power, and it's still going to be 1. So it does not affect the rate at all. The rate itself in these reactions would be equal to the rate constant. Other reactions, in first order reactions, you have the concentration raised to the power of 1. And this means that doubling the concentration or increasing the concentration will increase the rate by that same factor. So in the case of doubling the concentration, if you double the concentration, it's 2 to the power of 1, so 2 itself. You double the concentration, and therefore the rate is doubled as well. This is a first order reaction. And the last of the ones that we'll really look at is a second order reaction. And these are reactions where the concentration and rate is based on the concentration raised to the second power. So it's the concentration squared. And that means if you were to increase the concentration, the rate itself would increase by that factor squared. So a simple case is to double the reaction or double the concentration. And when you do that, you're squaring that factor of 2, which will lead to a factor of 4, 2 squared. And overall, the rate would then increase by 4 times, and the reaction time would decrease by 4 times. There are other reaction orders. These can keep going on for a number of times, third order, fourth order reactions, but in experiments like this one and in this level of chemistry, these are really the only 3 that would be focused on in class and things. So I'd mentioned earlier that the kinetics is important, looking at, and the thermodynamics. They're tied together in how the reactions happen. Many times there are a lot of different reactions that have 2 outcomes or more than 2 outcomes, but which products are favored and which products will actually form, these can vary. And there are 2 different types of products that you can see. There can be either the kinetic product, the one that happens the fastest and the easiest, and the thermodynamic product. This would be the one where, in the end, overall, it's the most stable product. So in this reaction scheme that I have here, the energy needed for the reaction to get to product A, this first red line, is very small. It does not need a lot of reaction, or I'm sorry, a lot of energy to go through this reaction. And in the end, the product is at a lower energy than the reactant, so yes, that can happen. And that would happen fast. There is a low activation energy. However, the other line, this blue line of reaction B, you're starting off with the same reactants. There's a really high activation energy, but overall, the energy of the products is lower. There is less energy associated with these products right here. So this is the one that would happen if there was infinite time. This is the thermodynamic product. Given infinite time, this reaction will always go towards reaction B. However, in the short term, reaction A would be the one that would happen at least first because it has the lower activation energy. And knowing the difference between these two types of products can play a role in chemistry and figuring out if you want to push a reaction to one or the other, you need to know what the activation energy is, what the end energy is, and which of these products would either be favored by kinetics or favored by thermodynamics.
As mentioned, kinetics is the study of the speed of a reaction, the rate at which the reaction happens. Many times there can be multiple reactions that can occur. Different reactants can combine and form one product or another. Some reactions happen very, very fast. Others happen very, very slow. And the difference between them is how thermodynamics and kinetics are related. Something that does not take a lot of energy, it's easy to undergo, but overall the end product is a little not very favored. That would be the kinetic product. It's something that, yes, it can occur and it's really easy to get to. The thermodynamic product many times is the one that has the lowest possible energy. You're looking at the products that have the lowest amount of energy, where it might take a little bit of extra energy, a little bit of oomph for it to actually go from the reactants to the products, but overall in the end, it will happen. It will get to that lower energy level product. That's the thermodynamic product. But that activation energy, that energy that it takes to get to those final products is dependent on the kinetics, or that's what the kinetics is based off. Overall, if a reaction will happen is based on the thermodynamics, but when a reaction happens is based on the kinetics.
The specific reaction that you're looking at in this experiment is the kinetics of the iodine clock reaction. And this reaction is a combination of iodate ions and bisulfite ions to form molecular iodine, I2. And it, by the presence of an indicator in the solution, it forms an intense blue color. The starch in cornstarch shows up as a dark blue color when it reacts with any iodine that's present, and that's what you'll see in the reaction. Overall, this reaction is an oxidation reduction reaction, where the iodate ion is the iodine in that is being reduced to molecular iodine, I2. The bisulfite ion, the sulfur, is being oxidized to a different oxidation state in the sulfate ion. Looking at the two sides of the reaction, you have the iodine present in iodate is in the 5+ oxidation state. And to get it down into the neutral molecular iodine state of 0, it would need 5 electrons. But there are 2 iodines in this balanced equation. So you would need a total of 10 electrons for this to occur. On the oxidation side, one of these sulfurs in the bisulfite ion is in the 4+ oxidation state, and it needs to get to the 6+ oxidation state within the sulfate ion. And in that process, it loses 2 electrons. The reduction of iodate needs 10 electrons. The oxidation of bisulfite only generates 2 electrons. So you need 5 of these reactions to drive 1 of these reactions. So when you multiply that by the entire reaction by 5, multiplying everything, you have this overall oxidation reaction. And now the electrons that are generated are equal to the electrons needed. In the end, you have 5 bisulfite ions reacting with 2 iodate ions to generate only 1 molecular iodine molecule, 5 sulfate ions, 3 acid ions, and 1 molecule of water.
The main video reaction looks at the reaction between potassium iodate and sodium bisulfite. In the first trial, 50 milliliters of potassium iodate solution is reacted with 5 milliliters of sodium bisulfite solution. There's a delay in the reaction based on the kinetics of the 2 reactants. After some amount of time, the reaction will begin to show its products of iodine, forming a blue color.
Now, in that reaction video, you saw the reaction. You saw it going from the colorless solutions into that dark blue iodine solution. And that you notice that delay. So in this reaction, what we're doing, or in this experiment, is we're varying the concentration of iodate. So initially, you're going to have different concentrations of iodate ion, and you're going to be timing how long does the reaction take. How long does it take from the time those 2 are mixed together until the solution turns blue? And when you do that, you're going to be measuring the time and calculating the concentration. You're going to be looking at that rate law. And with the concentration of bisulfite being constant, that is just some constant number. So the rate is going to be that constant multiplied by the concentration of iodate raised to whatever that reaction order happens to be. And this is what you're looking for in this experiment. You're calculating and determining the reaction order based on a graphical method, or you're going to be graphing this and determining the reaction order. So to do that, you're trying to figure out how can that reaction order actually be determined? And you're doing this through the use of logs and through the use of a graph. So the first step is you have the rate law itself. The rate will be equal to a constant value, which is the rate constant times the constant concentration of bisulfite ion, and then multiplied by the concentration of iodate raised to the reaction order. So the rate is equal to 1 over the time. So the time is how long it takes for one reaction to happen. The rate is how many reactions can happen in 1 unit of time. So they're inversely proportional, and you can substitute that in. Time is what you're measuring. In a lab setting or in a video setting, time is what you're measuring, not the rate itself. Once you have that substituted in for the rate, you can take the log of both sides of this equation. By taking the log or the logarithm of both sides of the equation itself doesn't change. You're just adding a log to both sides, so it's still equal. But with the properties of log, you can factor out that exponent, that reaction order value, out front. So you no longer have to utilize something raised to a power. Using the properties of log, you have the log of 1 minus the log of time will equal the log of some constant plus the reaction order times the log of the iodate concentration. And since the log of 1 is 0 and the log of a constant is still just a constant, you can make this equation look like the equation for a straight line. You have the negative log of time equals the reaction order times the log of the concentration plus a constant. This is a straight line now. It's in the format of y equals mx plus b, the equation for a straight line. So you're going to be plotting the negative log of the reaction time as the y value, the log of the concentration of iodate as the x value, and then solving for that slope. And that slope is going to give you the reaction order. So when you make this graph, you're looking at, again, the negative log of time on the y-axis and the log of iodate on the x-axis. These, when you're doing it this way, you're using measured values, and measured values are never exact. So the reaction order is either going to be 0, 1, 2, 3. You're looking for that whole number reaction order. And the slope will not be a whole exact number. So when you're using real data, you do have to interpret that a bit. You're looking for the closest whole number to the slope of this line. Another thing to point out with the graph that you're making is that both the negative log of time and the log of the iodate concentration will both be negative values. The iodate concentration is, the stock solution is approximately 0.02 molar. So these are values that are lower than 1. So the log of that is going to be negative. You're plotting this value or plotting this graph in the lower left quadrant of the Cartesian plane. So both of these scales will be negative. The other reaction to investigate the kinetics for is the reduction reaction of permanganate by sucrose or table sugar. And the video for that can be found here. Overall, in this reduction reaction, the permanganate ion, MnO4- is reduced by sucrose in a two-step reaction. In the first step, it gains one electron to form the manganate ion, or MnO4 2-. And in the second step, which is much slower, it forms that manganate ion gains two additional electrons to become the manganese dioxide molecule. Each of these different forms of manganese shows a unique color, and you can look at this through the observations in the video. When we look at the both of the half reactions individually, both the reduction and the oxidation, we can start by looking at the reduction of the permanganate. And this is what's giving off the color and shows you that the reactions are taking place. The first step of the reaction happens very, very fast. And in the video is the one that's investigated second, because we need to dilute the concentrations in order to even see it. But in this first step, the permanganate ion, which appears as a dark purple or in lower concentrations, more of a magenta or a pink color, is in its 7+ oxidation state. It gains one electron from the sucrose and is reduced to the 6+ oxidation state. And this gives kind of like a green, blue, almost teal type of a color of the manganate ion, MnO4 2-. And this again is looked at second because initially it happens very, very fast. The first step, however, the first reaction that the video looks at is actually the second step of the reaction, because this can be done at more manageable concentrations without having to dilute them. You can see that the green, blue, or teal manganate ion will gain two electrons to form manganese dioxide. This is actually a black, very, very fine powder that's dispersed throughout the liquid, where it appears kind of like a golden brown type of a color. And in both of these reactions, this is occurring under basic conditions. So you have here the balanced reduction reaction of manganate to manganese dioxide under basic conditions. And in the video, in that first part, the first section of the video, you're looking at the second step, and you can time how long does it take for it to go from green to golden, and compare that to the concentrations given. And in the second part of the video, the concentrations are cut down by quite a bit, and looking at a much more diluted reaction where you can see this first step much more clearly. And again, you're timing how long does it take to go from this pinkish purple color to the teal green color. While not directly in the lab report, this is a redox reaction, and we're looking at the reduction of sucrose. But for a reduction to happen, an oxidation reaction also has to take place. And this oxidation reaction is that of sucrose. Sucrose is table sugar, and that's this molecule that you can see right here. And on one sucrose molecule is 3 of these groups right here, CH2OH. This is a primary alcohol group. And in this primary alcohol group, the carbon is in an oxidation state of -1. There's 2 hydrogens around it and an oxygen right here with a hydrogen on it. So the overall oxidation state of this one carbon would need to be -1. And this gets converted or oxidized to what's called a carboxylic acid group. And in this form, the carbon has an oxidation state of 3+. So in this oxidation reaction, each one of these groups will lose a total of 4 electrons. So overall, one molecule of sucrose will lose 12 electrons, which it can give to the permanganate ion to convert it first to the manganate ion and then to the manganese dioxide solid.
Overall, you're looking at a few different chemical reactions. You're looking at how concentration can affect them, whether it speeds it up, slows it down, but also looking at the specifics of how it affects the reaction. Is it a first order reaction, a second order reaction, or even a 0th order reaction where the concentration doesn't matter at all? You're looking at these reactions, you're timing them and figuring out how fast these reactions happen, how that relates to the concentration, and overall, what is the rate of these different chemical reactions.